recall that we've learned different operations on functions, just like we have different algebraic operations on real numbers, where you can add two real numbers to get one real number, you multiply to get another number, you can divide to get another number, and so on. For functions, we can't add two functions to get another function. The conditions are simple. So if I give you two functions f and g, and I want you to find the sum of f and g, so f plus g will allow you to act on x. Definition is that this is f of x plus g of x. All right. Since we shall be talking about f of x, it means x is an element of the domain of f. We are also talking about g of x, meaning x is an element of the domain of g. So for this operation to make sense, that means for f plus g to make sense, this argument x must be an element of the domain of f intersection the domain of g. Whenever this intersection is not empty, we can always discuss f plus g. But if the intersection is empty, it does not make sense to talk about f plus g, because it must act on x, meaning x has to be in the domain of f for us to have this. X also has to be in the domain of g for us to have that. So with this now we have other operations. We can do f minus g acting on x is f of x minus g of x, provided the domain of f intersection the domain of g is not empty, so x is there. We can also do f divided by g acting on x. This is f of x divided by g of x, provided g of x is not the zero function, is not zero. And then here again, we want x to be a member of domain of f intersection domain of g. So we still want non-emptiness of this intersection. We can deal with f times g acting on x to mean f of x multiplied by g of x. Again, we want x to be in domain of f intersection domain of g. All right. Now, we want to deal with how to compose two functions or three functions to be able to get a new function. That's our interest here. If f at x is equal to 2x plus 1 and g at x is x to the 3, so f plus g acting on x is simply 2x plus 1, then plus x to the 3, which we can of course rearrange respecting the power. We have x to the 3 plus 2x plus 1. Notice here that the domain of our f, dom of f, is the whole of R. The same thing is true for the domain of g. It is also the whole of R. And of course, when you intersect the set with itself, you get the same set. So the intersection is not empty. So we can talk about f plus g acting on x, and that gives us this. So this is the new function we have when we add f to g. Using this, you can deal with other operations, except that of composition, which I want to expose now. All right. First of all, give a diagrammatic picture or a picture of what we shall be dealing with when we worry about composition of functions. Say D. We want f here, we want g here. So by this arrow, what I mean is that f is a function defined on x into y. G is a function defined on y into the set D. To compose f with g, that is f composed with g, we must allow this to act on x. And what this means is nothing but f acting on g of x. Alright. G of x by this diagram is an element of the set D. F is defined on x into the set y. So for us to talk about f of g of x, it means that g of x must be an element of the domain of this function f. That is one thing you must put at the back of your mind. Once you write this, write explicitly what it means. So that will now give you an idea of where g of x lies and where f is taking its values from. That means the domain of f. So for this to make sense, we would demand that g of x, in our own case here, is a member of D. And then for this to make sense, D has to be a subset of x. If D is a subset of x, it means that g of x is a member of capital X. And that means g of x is in the domain of the function f. So f can see g of x and act on it. And so what are we saying? What we are saying in essence is that for this composition to make sense, then range of the function g intersection the domain of the function f should not be empty. In fact, of course, this is, we must demand rather that the range of the function d intersection the domain of the function f should be a subset of the domain of f. It can be the whole of the domain or a proper subset, no problem. So, when this happens, then f composed with g makes sense. If the range of g intersection the domain of f is not a subset of the domain of f, then you cannot talk about this composition. It doesn't make sense. So here, with this diagram, for this composition to make sense, we demand that this is a proper subset of x, or it is even the whole of x. Otherwise, nothing to give as meaning to f composed with g. That's one way to compose. We can also compose the other way around by thinking of g composed with f acting on x. Again, by definition, this is nothing but g of f of x. That says that f of x must be a member of the domain of g. Again, for this to make sense, we demand that the range of f intersection the domain of g must be a subset of the domain of g, at least. If this is not true, of course, we know that when you take the intersection of two sets, if I give you sets A and B, so A intersection B is usually a subset of the two sets, is also a subset of the set B. So we need this to be a subset of the domain of f. This is always true. And then we need this to be a subset of g, which is also always true. And then more importantly, this does not have to be empty. This does not have to be empty.